From the Library of Congress in Washington, D.C.
Good morning. I'm Jennifer Harpster. I'm a research and reference specialist with the Science Technology Division here at the Library of Congress. I'd like to welcome you to today's program, Dawn, a journey to the beginning of the solar system. This program is part of a series of programs or series of lectures presented through a partnership between my division and NASA's Goddard Space Flight Center. I'm also happy to report that this is the 9th year that the library has been partnering with Goddard. And I also want to remind you of our last program of the year, and it certainly is not to be missed if you're into Pluto. On Tuesday, December 8th, from 11:30 to 12:30, right here in the Pickford, Dennis Reuter, he's an astrophysicist and an instrument scientist for the NASA's New Horizon mission. He's going to be highlighting some of those first close-up images of Pluto, so it's going to be a highly illustrated lecture, and I hope you can attend. But today we are learning about the Dawn mission to the giant asteroid Vesta and the dwarf planet Ceres. It's my pleasure today and an honor today to introduce today's speaker, Dr. Lucy McFadden, a planetary scientist who investigates the surface composition of asteroids, comets, meteorites, as well as our own satellite, which is our moon, and those moons of Jupiter. Dr. McFadden is currently a co-investigator on the Dawn mission, which seeks to unlock some of the mysteries of planetary formation by studying Vesta and Ceres. She also leads Goddard's higher education and university programs, facilitating the training of the next generation of STEM professionals for the Sciences and Exploration Directorate at Goddard. Dr. McFadden received her undergraduate degree at Hampshire College in Amherst, Massachusetts, where she took a class on optical and radio astronomy that changed her life. She received her master's degree in earth and planetary science at MIT and a doctorate in geology and geophysics from the University in Hawaii. So when I was writing this introduction, I had a really hard time picking out all these accomplishments to highlight that Dr. McFadden has done so far in her amazing career. So I thought I would do some cliff notes. One of her accomplishments is she is a founding and past director of the College Park Scholars Program, Science Discovery in the Universe. She also is the co-editor of the Encyclopedia of the Solar System, the first and second editions, which we have in the Science Reference Collection. She also is a research professor from the Department of Astronomy at the University of Maryland. She was a member of the science team for the Near-Earth Asteroid Rendezvous mission, which orbited and landed on the asteroid 433 Eros. She's a co-investigator on the Deep Impact mission that investigated comets. She's also collected meteorites in Antarctica, and she has an asteroid named after her. Asteroid 3066 is named McFadden. So please now join me in welcoming Dr. Lucy McFadden to the Library of Congress.
Thank you, Jennifer. It's a pleasure to be here and an honor to be invited to give this lecture today. And I just hope you'll share the journey and the excitement of discovery that my team members and I have engaged in the past numerous years. It's actually been a 15-year journey. I was sitting here staring at my cover slide and want to point out that the Dawn mission is a partnership. It's a NASA mission, but it's a partnership with scientific leadership at UCLA, and I'm going to read across from the bottom. It is managed by the Jet Propulsion Laboratory at Caltech. Our spacecraft, our little spacecraft that can and favorite spacecraft, was built by Orbital, which was merged a couple of months ago and is now Orbital ATK. We have instruments provided by the Italian Space Agency and the German Space Agency, DLR, and those are and the camera is managed by the Max Planck Institute, which is MPS, and the VIR is managed by Institut National for Astrofisica in Rome. So I'm part of a team, and I'm here to share what our team has done so far with you. Because it's a tough time out in the world, I want to give us some cosmic relief. Let's go out beyond Ceres and look back toward the sun. And I'm going to work my way out. So from the sun working out, you can see the inner planets, the terrestrial planets, Mercury, Venus, Earth with its moon, and Mars. And their orbits are drawn in here in this artist's rendition, just to remind us that everything in the solar system orbits the sun in elliptical paths. And then we have the asteroid belt, which our artist here has designated. And so you can see all these fragments of the asteroid belt that were growing into planets, but that planet growth was disrupted when Jupiter migrated in toward the sun and resulted in gravitational disruption that caused a lot of collisions, of which many and most of the asteroids are fragments from those collisions. But there are a couple of larger asteroids that have remained intact since the beginning of the solar system over 4.5 billion years ago. So here in the foreground in the lower right is a representation of Ceres as we knew it before we arrived. You can see it has some fuzzy little lobes around it. It sort of looks like lungs. And the Herschel Observatory, European Observatory, has observed a couple of years ago some evidence of outgassing of water associated with Ceres. So we were eager to get to Ceres and see what the Dawn mission could reveal to us. Prior to getting there, we had used the Hubble Space Telescope. So again, a partnership of all the resources available around the world. We imaged both Vesta and Ceres with the Hubble telescope and observed it over time, and observed changes as it rotated. And you can see here slight subtle changes in the color for each object. And you should see first off that Ceres is more or less round, and Vesta is more or less not round, and it sort of has a bite taken out of the bottom. And it's for this reason that the IAU in 2006 deemed Ceres a dwarf planet, because it's round and gravitationally relaxed, and has cleared its region around it. And Vesta is still an asteroid. It's not gravitationally relaxed. It's not round. And we figured out why with the Dawn mission. So next, I want to pay tribute to our satellite, the spacecraft. We call it the Dawn spacecraft. It is powered by ion propulsion. Ions, it has a tank full of xenon, which is an inert gas, and the xenon thrusts out the ions behind it, and it gives the spacecraft an equal and opposite force in the other direction, and it thrusts and moves the spacecraft through space. We couldn't have done what we've done without this ion propulsion. Every thrust sort of gives the force of a piece of paper sitting in your hand, but that force is added up to the spacecraft. It keeps moving, and you get a little bit of change in velocity as it goes. And so over the 7 years of its time in space, it has thrust over 50,000 times thrust for 50,000 hours, for a total of about 5.7 years. And that has resulted in a high velocity that has allowed the spacecraft to get out to where we're going. with only using the mass of the xenon in the tank as a propulsion device. If we had used conventional chemical propulsion called hydrazine, it would have weighed too much, and we would have not been able to launch it at the cost of the Discovery mission. So our ion engines got the spacecraft to where it's going, but it took us 7 years to get there. So we traded off cost for time. But hey, it gave me a great, it happened at the right time in my career, so I was able to see it at the end. So while it's in space, the spacecraft is powered by solar panels. The spacecraft has traveled to over 3 times the distance from the 3 times the distance of the Earth to the Sun. So it's far away. It needs large solar panels to collect enough sunlight to get enough energy to power the instruments. So the solar panels are 65 feet long. To put that to scale, when I moved from Baltimore to California many years ago, I put my family's furniture in a moving van that was 70 feet long. It carried three families worth of junk or furniture, but to scale, that's like a long a 16-wheeler semi-trailer. Our instruments, or the eyes and ears and nose of the spacecraft, include a camera, a framing camera, that was provided by our German colleagues and led by Andreas Natus at Max Planck Institute. Our gamma ray and neutron spectrometers are American-made and headed up by Thomas Prettyman, who he built the spectrometers at Los Alamos National Laboratory, and he's now operating it from the Planetary Science Institute in Tucson, Arizona. And then our visible and infrared mapping spectrometers, built by our Italian colleagues, is led by Cristina De Sanctis, and they had it built with by an Italian company under Christina's direction, and they're now operating it. We also consider the antenna on the spacecraft as an instrument, because the antenna sends back signals that give us the precise location of the spacecraft. And from that information, we derive gravitational maps and information about the gravity field of our targets. And so that allows us to study the interior. So the antennas are sort of fourth instrument. We launched, so our spacecraft was launched on a Delta II rocket from Cape Canaveral. And have any of you ever had the opportunity to see a spacecraft launch? Do any of you think of, okay, good, what is better than watching a spacecraft launch? Never mind, we better not answer. But if you ever have a chance to, go to see a spacecraft launch, it's really pretty exciting. And this is a photograph of the launch at the launch pad at night. Okay, this is not a model, even though I have one on my desk at home. But this was it the night before we launched, all lit up. We went out to check on it, and the mosquitoes were horrific. So take DEET when you go. And then the next morning, we were fortunate to have the weather conditions such that we could launch. And we launched at dawn on September 27th, 2007. Okay, so here we are in 2015, 8 years later. Let me show you our path. So let's see, dawn launch is in at the Earth, and we spiraled out past Mars a year later, and then had a 3-year cruise to Vesta and arrived in 2011. Spent a year orbiting Vesta, and I'll tell you about that. And while Vesta itself moved in its orbit around the sun, so we spiraled around it, and left for another 3-year cruise and arrived at Ceres in March of 2015. Yes, so my story will not end yet, because we haven't ended the mission, and we're still in this interpretation phase, which you'll hear about shortly. So Dawn is the first mission to orbit a main belt asteroid. We had orbited a smaller near-Earth asteroid back in 2000, but this was the first main belt asteroid. And I think I just want to let this. Here's a summation of our observations of Vesta. So the spacecraft, the asteroid is rotating on its axis. 1 day on Vesta is 5 hours and 20 minutes. So we're lucky we don't live on Vesta. We'd never feel like we got anything done. So I almost want to say, well, what do you see as the spacecraft is rotating?
Shaped like a mountain.
It's shaped like a lemon. Good. There are mountains. There's streak down the center. There's something going across. I can play it one more time. I think I have time to play it one more time. There's streaks going around the equator or at an angle. Those are compressional tectonic features. Here's another set of lineations at the equator. We do see a lot of craters to begin with. And that mountain at the southern hemisphere, that mountain is a big basin. Oh, there are those three craters that sort of look like a snowman. We had a Christmas card and we put a snowman on it. Okay, so let's take a look at some of these features. I'm going to go down to the southern basin to that mountain, which is really the central peak of a large crater. It's, okay, there we go. Okay, so now we've taken our images with a digital terrain model that we derived from all the images and we color-coded it for the altitude from the center of Vesta, okay? So the blue is the deepest part of this basin, and it's 14 miles below the mean, sea level on the asteroid. They don't call it sea level, but the mean geoid. So it's 14 miles deep, and the peak of the mountain in red is 12 miles high. So this peak is more than twice as high as Mount Everest. Well, that's not surprising because there's not as much gravity on Vesta. Vesta is 250 kilometers across. If I were to lay that onto a map of the United States, it would sort of fit across the state of Texas. Okay, so this is a small body, so there's not much gravity. So if you have an impact and you have an impact and something rebounds without much gravity, it's going to get very big. But still, this was pretty spectacular. We saw evidence of it from Hubble, and when you think about it, you say, wow, it's amazing that Vesta's still intact, that it's still a whole body and not total fragments. Well, it turns out it was formed by huge impacts in the southern hemisphere, and debris from that impact created a family of Vesta asteroids, and there are hundreds of smaller asteroids that are about 50 kilometers across, 1/5 or smaller the diameter of Vesta, that are in orbits that are similar to Vesta. And in fact, throughout the age of the solar system, this probably happened 3 or 4 billion years ago. Some people say maybe a billion years ago. Smaller debris has been scattered across the solar system under gravitational influences from other planets like Mars and other asteroids. And in fact, there have been many pieces of Vesta-like asteroid fragments that have landed on Earth. And in fact, 1 in every 7 meteorites that we have in our meteorite collection is from Vesta.
How do you know that?
We know that from we take the meteorites in here that we have in our hand and in our labs. We shine a simulated sun on it and look at the reflected light that gives a spectral signature. It's like the fingerprint from these meteorites. They're called basaltic achondrite meteorites. We also We also name them HEDs because they have names based on the first type. That's probably extraneous information. But then, so we have the reflected signature. This is the thumbprint of these meteorites. And we look at the reflected sunlight from Vesta itself. And it has the diagnostic signatures of these reflectance spectra. So they are identical. That's the first reason. The second reason is that we have dynamical models. We can predict the gravitational changes, pushes and shoves throughout the age of the solar system that show that fragments from Vesta can migrate into a region of the asteroid belt, a resonance that will send them on a direct path to Earth. So that's the second. And then the third aspect is that we see trace amounts of fragments within these meteorites that we also see evidence for from the Dawn mission. So we're pretty certain, and there are no other large objects in the asteroid belt besides Vesta and the Vestoids, its family, that have these same spectral signatures. So then my colleagues, my geologist colleagues, got their hands on all the images from Vesta, and they start making geological maps. So they take, based on the surface features and the relationships of various flows and the density of the craters. So here's a geological map of Vesta with a time sequence. I'm going to start in the upper left. The green, the Marcia crater material is the most recent. It's young. There are very few craters on top of it, so it's the youngest material. Then the yellow and red to the blue is material from Rhea Silvia, which was the southern hemisphere formation. I'm sorry, I didn't bring a pointer. And oh no, here's a gavel. Whoops. So there's the Rhea Silvia material from that impact that was spread, and you can see it covered most of the southern hemisphere. Because most of that's blue material that covers part of the southern hemisphere. And then the Venonea, there's another basin beneath the Rhea Silvia basin. There are actually two basins. Oh, thank you. There's a formation beneath Rhea Silvia, that is the oldest material. So we have. There we go. So this is the oldest material is in the purple and the brown, which is cratered highlands, and we've also marked some of the tectonic features that are caused by the giant impact. Here are tectonic features from the older Venonea impact that go here. So we have the geologists who've we now have a time sequence, and we have spatial resolution that we couldn't see before. Another, I'm going to give you two other significant results from Vesta before we move on to Ceres. Here's the map of reflectance beyond the region where our eye can see, out beyond 1 micron, and this reflectance shows variations in brightness across the surface. Part of it is brighter, and here's a dark region in the center and another bright region here. We could see this from our ground-based telescopes, but we didn't know what it was caused by. So from the Dawn mission, I think we have a good idea. This dark material here also is correlated with the presence of an absorption feature in the spectrum that is due to OH-bearing species, so hydrated species. Not water itself, but hydrated species. So we got evidence from our spectrometer that this darker stuff has an absorption due to hydrated minerals. We also found correlation with a certain type of those basaltic achondrites, because they come in different flavors. Those meteorites that come from Vesta come in different flavors. Basically, three different flavors: blue, green, and red. But they have names: eucrites, howardites, and diogenites. But this region here of the eucrites is the ancient crust, and has more of this dark material in it. And these meteorites, when we look at them here at Earth, they also have small amounts of this dark material from carbonaceouschondrites that are dark and hydrated. And then our third evidence that supports this is from our gamma ray and neutron maps. I'm sorry I don't have them at the same scale. However, the footprint of this neutron spectrometer is much larger, so I can't give it the same detail, but you can certainly see in this region between about 60 and about 120 degrees longitude that this region has a overabundance of hydrogen-bearing material. So that's two instruments that give us this evidence of water-bearing species in it. And then my third set. So in summary, we have the giant basin-forming impacts, redistributed material all over Vesta. We have evidence of dark, hydrated, carbonaceous material, remnant from the earlier Venonea impact that is located, concentrated between 60 and 120 degrees longitude. And the spacecraft itself, while it was orbiting Vesta for over a year, from its gravitational model, was able to determine that Vesta itself has a metallic core. And that's also consistent with the formation of these basaltic achondrite meteorites that we have, because they have had all their metallic iron removed from them. So in many cases, Vesta has many similarities to a very small, tiny terrestrial planet. It has an iron core like the Earth. It's way tinier than the Earth. It has evidence of basaltic volcanism. Silicate-rich material has been heated during the life of Vesta, heated and flowed out on the surface, just like volcanic flows here on Earth. And then the impacting that occurred throughout the early or the older times of the solar system has redistributed the material and sent some of it here toward us on Earth. So Vesta is very similar, has similarities to a terrestrial Earth-like planet. We just finished publishing that work, and it came out last spring, and that took us a couple of years, and we made good use of the time while the spacecraft was cruising on to Ceres. So let's go on to Ceres. So it's the first spacecraft. It's our second first of the Dawn mission. Arriving at Ceres, we went into orbit on March 6th. The first thing we did, and this was a project that I led, was to look for moons around Ceres. We also looked for moons around Vesta. We didn't find anything down to about 30 meters on Vesta, so there's nothing orbiting like a moon around our Earth or around Mars, which has two moons. So at Ceres we looked, and here on the left is a night sky projected at the same scale as our camera on the Dawn spacecraft. And we've highlighted a couple of stars here, and you cannot see Ceres, but here on the right is an image on approach to Ceres taken by our camera, and it's not pretty because I want to look at all the flaws and everything and make sure that I know what I'm looking at and make sure I'm looking for a tiny object that's moving around Ceres. So I'm looking at everything and checking everything that we see and make sure it's either an artifact on my camera or something, or an object, a star, or something with motion. Now if I just look at one, so I've highlighted some of the objects. This is an artifact of the readout on the camera. It's a CCD camera, and we just can't, there's so much signal here it doesn't get read out clearly. This is circled in red as an artifact on the image. We took hundreds of images, and we devised a method where we add the images that in time, focusing on Ceres. Here we've got Ceres off at the edge. We're not interested in Ceres, but here we've added 64 images that are registered on Ceres. And since the spacecraft is moving in space, these background stars will move themselves, and so they form trails. So then, with this image, we're set with looking for things that are moving in a different direction, but have the same pattern as the background stars. So then we scan these registered images looking for something going in another direction. Does anyone see anything that's moving, that's skewed from all of those others? There's maybe that one. Yeah, but what's wrong with that? That's only one dash. There has to be 4 of them to be real. Well, we scan it completely. Here's another, these are cosmic rays. Here's a single spot, that's a hot pixel. So we've scanned these, and unfortunately we haven't found anything. But then we say, well, how deep can we see? And so we calculate the brightness of the faintest asteroid, assume it has the albedo of Ceres, and we determine that we've searched the space around Ceres down to between 20 and 300 meters in diameter. So unfortunately, there are no moons around Ceres either. So here's some basics, things to know about Ceres. It rotates more slowly than Vesta. It rotates about once every 10 hours. It's about 590 miles across. Oh, and now I have to correct myself. On a map of the United States, it's Ceres that's almost 1,000 kilometers that's the width of Texas, and Vesta is the width of the state of Arizona. Okay, so sorry about that. The surface temperature at Ceres is between 130 and 200 Kelvin, where 300 Kelvin is temperature at Earth. Okay, so it's cold. That's important because if you had water ice sitting on the surface of Ceres, it would sublimate. It's not stable. However, Ceres as a whole has about 25% water. Someone please ask me, how do I know that? Yeah. How do I know that? Thank you. That was determined from the relationship between its density and its shape, derived from Hubble observations. It is basically round. You're looking at it here, is basically round. However, when you carefully measure its axis of the equatorial to the polar axis, it's not perfectly round. The Earth is oblate, but Ceres is a little bit inflated. It's a little bit inflated. And that, combined with knowledge of its density, which is 2.1 grams per cubic centimeter, whereas the Earth's crust has a density of 3.3 grams per cubic centimeter. That density being less than 3 tells us that there has to be a significant amount of water in the whole bulk composition of Ceres. Yet, if water were on the surface, it wouldn't stay, it wouldn't remain. So from our thermal models that my colleagues Tom McCord and Julie Castillo have done, it may have some liquid water in its interior, but not on its surface. And the surface reflects only about 10% of incident sunlight. It's basically dark. Vesta, in contrast, reflected 36% of the sunlight that hits it. Many of you may have seen, we did make the papers last spring for these 2 bright headlights, so those are big. I will talk about those. There are a couple of other bright spots that we see. There's some smooth plains, but it is a cratered surface. But still very different from Vesta. So let's see what we've learned. So our geologists, our mappers have created our map. And, ooh, I'm sorry, this one doesn't have, this is 0 degrees longitude over here and 360 over here. There is a big bright feature that is right on the edge, so sometimes we project it differently. Here's the bright crater that has bright material in the center, but also ejecta, bright material that's been ejected from it. Looking at this, is this something that came from outside and hit, when it hit, it splat and it's bright material? Or is it something from inside of Ceres, when it hit, was brought up from beneath the surface and spread out? So that's a question that you may have, and a question that the scientists too are having. Then we have, looking at the edge, as Ceres rotates around, we saw this little lonely mountain. This is 3 kilometers above the sphere, and it was initially called the pyramid. We quickly got to talk to the International Astronomical Union, who approves our names, and we gave it a name of Ahuna Mons. And all of the features on all of the craters on Ceres are named after the goddesses or gods and goddesses related to the harvest, because Ceres is the goddess of the harvest. So we're now in the process. My postdoc is modeling the distribution of the height with respect to this mountain, to try and determine what type of mechanisms could produce this. We see that the top here, the top flattened part of the mountain, is similar to the surrounding cratered terrain, and these are very steep slopes, and so it looks like it's an extrusion, something that pushed up from beneath the surface, and did so relatively recently, because all these steep slopes are pretty fresh. But we're working on an interpretation of that formation mechanism. Then here's our close-up of the bright spots, which exist inside the crater named Okator. And so this is quite a nice high-resolution image. The 2 bright spots resolved into about 8 other smaller spots with debris spread around it. When I look on my screen, I can see in the center here, seems to be something that's dome-like right in the middle. And we have determined the brightness. This material reflects 50% of the light that hits it, whereas the surrounding reflects 9 to 10% of the light. It's clearly inside of this crater. These crater walls are interesting. They're not quite, most craters are circular, but this has a lot of structure in it. And that tells us that the surface of Ceres has some strength. But it's not a lot of strength, because you get collapse and things falling. There's also some, at least on my screen, I could see cracks. Oh, maybe they're here. So the science team is really in the process of trying to figure out what this means and coming up with a good story that fits with the physical mechanisms. Yes, you?
Are there any theories at this point?
Well, yeah, we have general theories. It could be something from outside or it could be something from beneath. And help me, what do you think of? What are the first things you think of? Because guaranteed those are the same things that we think of. Sulfur, okay, because that's bright. We know it's bright. That's certainly one possibility. Anything else? What else is bright? I mean, the ice, we look at the ice, even though our thermodynamic models tell us that ice is not likely to be there, we're certainly going to look for the spectral signature of ice, of water ice. Maybe some other ices. There's some, yes?
Do you get any information of what, the material is by shooting getting spectral.
Right, we do have the spectra, but we're in the process of interpreting that, and the science team right now is having discussions about the interpretations. So there's one other thing. So think about on Earth, there's a place on Earth. Salt, yes.
Oh, carbonate.
Salt, carbonates, that's a good one too. Those are good too. And so the silicates, I think the silicates give the whole body the strength. But again, they could be different. There are many different kinds of silicates, so it could be something unique. And so the science team, literally, as I'm speaking now, is having a mineralogy working group discussion about the possible interpretations. So I don't have an answer, and it's not an easy problem. Our spectrometer does have spectra of these, but we're still there's no point in releasing the spectra until we have an interpretation to go with it. So I'm going to have to ask for your patience, and they're under discussion. Now, what we have released today is our mosaics of both the north and south polar regions on Ceres. So these are mosaics that were put together from our high altitude mapping orbit. And I guess I should have said that we have mission phases. We have the survey where we're at 4,700 kilometers. No, we were more than that. We were 12,000 kilometers at survey. Then we went down to high altitude orbit. We literally spiraled down. And these are mosaics from our high altitude orbit, which is about 2,700 kilometers, if I remember correctly. And in the North Pole, we found one more mountain. We've named it Yosolomons, and so Ceres now has 2 mountains, and we weren't expecting any, but there are 2. But why only 2? And then here, and as I stare at this, the more you stare at it, I see sort of some maybe large basin edges, rims of basins. But again, our geological mappers will be looking at these and building geological maps. In the southern hemisphere, okay, here's this large crater that may be called a basin, and then some other ridges, and it will all be large craters with smaller craters in the middle with peaks on them. And then this is a region with no data at all because of the viewing geometry. Now, an interesting thing. So this is now it's winter at the South Pole. So these were taken at Ceres summer. So an interesting thing. I think I have a minute to do this. Is on the Earth, our seasons are controlled by the axis at which the Earth tilts, the 23.5 degrees. Ceres tilts only 4 degrees on its axis. So we shouldn't get much of a season, except that the orbit of Ceres itself has a 10-degree inclination with respect to the Earth's plane, with respect to the plane of the Sun and the Earth. So this 10 degrees tilt, and the fact that Ceres is down here now prevents the sunlight from getting to the whole southern hemisphere. That it would change if we were up here. So that's here. I do have some of my spectral imaging. Again, no spectra, but our spectral imaging spectrometer has 800 channels of data, and in each channel you get an image of Ceres. Now this was Ceres on approach, okay, so we were far away, but look at this sequence of visible, infrared, and thermal. These are 2 different spots. Here you can see a bright spot here, and this is actually Okator. And in some displays, you can see that the infrared is a little bit brighter in Okator. It's a little bit red. And then here it's clearly dark in the thermal. So that means that it's colder in this thermal image than everything else. So it's reflecting much of its light such that it's cooler than the surroundings. Now down here at this bright spot, which I believe is Haulani crater, it's bright in the visible, it's bright in the infrared, but it's also bright in the thermal infrared. So it's bright and hot, whereas Occator is bright and cold. Now that's a clue too. That's going to, when we untangle our interpretations, we have to take into account that not all the bright spots on Ceres are the same composition or the same material. So there's things going on, but unfortunately we just sort of say, huh? We're not quite sure yet. And in fact, I was just last week at a meeting in down at National Harbor, and someone tweeted saying, I just looked at someone who'd heard the results from Ceres, and they were staring blankly. And they said, I don't get it. And the science team is in the same situation. We'll just have to argue back and forth and arrive at something. So Ceres on the interior, I'm mentioning there is evidence that that instead of water, we may have, well, we know we have water, but there may also be ammonia, ammoniated species, ammoniated silicates. And our thermal models give a possible internal structure that's similar to this, with an icy mantle and a rocky core, and there may be some liquid water present, but we won't be able to detect that. Now, with the fact that we're trying to create a coherent story about the surface composition, the processes, the active processes that form the surface of Ceres here, we're questioning now whether, with the fact that we don't have a lot of icy material on the surface, and that we find ammoniated species that come from farther away, that are stable at the outer parts of the solar system, we're asking ourselves, was Ceres formed here in the asteroid belt? If it was formed in the asteroid belt and it picked up some of these colder ammoniated species from the outer solar system, was that material deposited onto Ceres in the early solar system, or was Ceres itself formed far out beyond in the outer solar system and migrated in as a complete body? We hope we'll have some answers, but those are our fundamental questions right now.
Where is Pluto on this depiction?
Over there. Okay. So today the Dawn spacecraft is in the process of, these are orbits of the Dawn spacecraft as it spirals down. So at the end of October, we began our descent into our low altitude mapping orbit. We're probably down maybe around here, and we will continue spiraling down to an orbit of 850 kilometers. And in mid-December, we'll get our highest resolution images, but we'll also get results from our gamma ray and neutron detector, which will give us some compositional information, elemental compositional information. We'll know about the distribution of hydrogen to see whether these species are hydrated. Hopefully we'll be able to get some ratios that will allow us to disentangle the carbonates. There are some signatures due to carbonates. There are also signatures due to ammoniated silicates or clays with ammonia in them. So we do have more data coming back to us until the end of June, and we have an opportunity in the spring to write a proposal to NASA headquarters to ask for an extended mission, where we would plan to see what we can do if we stay longer, and if we can target certain areas with certain sets of instrumental observations to try and resolve some of our ambiguities. What's keeping us going are the engineers who have been keeping track of our fuel levels. We had, throughout the course of the mission, we've had some breakdowns. They haven't been catastrophic, but we had reaction wheels that failed, so that the stability of the spacecraft is not what it used to be. So we're operating on 2 reaction wheels instead of 4, and the navigation team devised a method to save our hydrazine fuel, And so at LAMO, we're going to start using the hydrazine fuel to stabilize us so that we can get clear, stable pictures. So here's our fuel tank. We're half full, and we're going to use it all up before the mission ends. As I said, I just want to give a shout out to my teammates. This was definitely a team effort. We're from all over the world. We meet a couple of times a year in person. We spend time on the phone every week, and then sometimes some of us dress up pretty well, especially when the Air and Space Museum gives them an award for achievement in space. And this is our project and navigation team a couple of years ago, 2014, when they received an award for their efforts at Vesta. So thank you for your attention, and we have materials on the website for your information.
So we'll do a short question. Carrie, can you repeat the question for them?
Sure.
The questions, I'm sure.
In the back, the gentleman in the back had their hands up first, and I'd like to alternate between taking questions from men and women, if possible.
In Vesta, you've got the real huge crater at the bottom, but you've got a big, huge crater up at the top. Could it be that the mountain on the bottom is a push-out from the bottom from the hit from the top?
Right. We've thought about that. Is it antipodal?
Yeah.
Is it opposite? And I think the gravity models do not support that.
Okay.
But we definitely looked into that. But we didn't see evidence of that.
Okay, thank
Oh, and I should have repeated the question, which was, is it possible that that there can be an effect from the giant impact in the southern hemisphere that's observable 180 degrees opposite it in the northern hemisphere? Okay, so I'll follow directions. Okay, gentleman to his left, and then I'll come down here.
You said that the propulsion, is it just releasing pressure out of the tank? Is it actual burning of the fuel? Or I think you suggested that it's just using the mass of the propeller.
The propulsion, okay, the question,
Then how did it slow when you got to the planet to actually orbit it? Because I know when Pluto it was a flyby.
right,
It didn't slow it after making a long trip. But
okay. So the question was about the fuel and what the mechanism is of producing the thrust on the spacecraft. And then the second part was, how did we slow it down? So the fuel is sending the ions, the xenon is ionized and forced out the back. It's forced out through the nozzle of the ion engine as a charged xenon particle. And xenon's heavy. It has mass, and it's accelerated through magnetic fields. And that gives it a force. So there's no chemical reaction that produces the energy. It's produced by magnetic fields and the direction in which the thruster points. And that causes the spacecraft to go in the opposite direction. And what we do is match the orbit. So we are thrusting away from the gravitational force of the sun. And so we're spiraling out the whole time. And then we match orbits with our targets. So, and the thing is, the thing that's hard to grasp is that this is just tiny little changes with every little puff, every little ejection of the xenon ions. And it's just that it took 7 years. And so we didn't really have to slow it down. We just matched the orbit. We get there. And then also we change directions. You have to change the vector, so you move the engines and point them in a different direction. So that's actually how we do it. It's pointing the direction, but it's always a thrust.
when you got there, gravity pretty.
Well, when we got there, in fact, we had a hard time saying, when do we go into orbit? We had to declare it because everybody wanted to say, okay, now we're in orbit. But But Ceres is moving around the sun, and we sort of caught up to it. So it's more like a dance than driving there. Yes, sir.
You mentioned trying to get money to extend the mission, and I heard the same thing in the news about the Pluto.
Yes.
Is it really an option at NASA not to get every benefit of these expensive and rare assets in space?
Well, the fact is, we're going to be competing. There's a number of missions that are competing, and they have this senior review where we write a proposal, and we have to have compelling science, because it's your taxpayer dollars and my taxpayer dollars, and it's a finite budget. So we can think of a lot of things to do, but if we do an extended mission on something, then we have to delay starting something else or not do something else. So it's all a matter of balancing the budget. Is that correct, according to the people from NASA headquarters in the audience?
Yes.
Thank you. And I forgot to repeat the question again. We'll play Jeopardy. On those of you doing the webcast, we'll play Jeopardy. Yes, ma'am.
I was intrigued by what you said the difference in reflectivity between Vesta and Ceres was, and just from reflectivity of all the stuff in the asteroid belt, is Ceres an anomaly, or can you tell what the basic composition of the crust is on these bodies?
So the question was about the differences in the reflectivity of Vesta and Ceres and other things in the asteroid belt. And can we does that tell us anything about the composition? So the reflectivity, or the brightness, it's also called the albedo, how white it is, because albedo is the Greek word for white. So it constrains the composition, but there are many things that are bright that reflect 50% of sunlight, and so salts, sulfates, and ice, but they can. We need other instruments and other information to constrain those differences. So we're very much waiting for the interpretation from the spectrometer to see whether there are spectral signatures of ice or sulfates or water frost on the surface. And then the difference between Vesta and Ceres, most of the asteroids are dark, like Ceres. In fact, many of the asteroids are darker. They reflect about 3% of the light, and that's less than a charcoal briquette reflects. So Ceres is dark, but Vesta is very bright. And again, the differences, I forgot to tie in. I said that Vesta was like a terrestrial planet, a small terrestrial planet, but Ceres has a lot of volatiles and unusual species that are stable at colder temperatures. So there's a temperature regime difference in these different parts of the asteroid belt that plays a big role in determining the nature of the surface and the composition of the material. So temperature is a big difference. Yes, ma'am, in the back.
For those who are interested in looking at the relevant data sets for these two sites, is it easy to find the data sets within those?
Okay, the question was for those of us interested in seeing the relevant data sets, is it easy to find them? These two websites are education and public outreach websites. So there's images available that have been released to the public, and educational material that's been designed by educators for various levels of grade levels. There is a process of placing the data in an archive, the National Planetary Data System Archive, and that takes time. We deliver it within 6 months of receiving it. So some of it is delivered, and that's a different website, the Planetary Data System website, which has the archived data, the raw images and the spectra, and documentation that explains it. And those are available for scientists worldwide or amateur scientists. They're available for anyone. to use. Thank you for asking. Yes, sir.
Iron core in both cases?
No. Iron core in Vesta, because its bulk density is about 3.5 grams per cubic centimeter, more like the crust of the Earth. But the core of Ceres has to be silicate rich. There's not a lot of iron in it, just because its density is lower. Its bulk density is lower. So we don't anticipate a metallic core in Ceres. Yeah, and that's a good question. Where'd the iron go? Maybe all the dark stuff, maybe the iron particles bring the albedo down. Thank you for asking that question. That made me... The question was what's the composition of the cores of the two objects? Okay, in the back, sir.
You said the Ceres had a skew from Earth's plane by 10 degrees. Is it alone in that? Is the rest of the asteroid belt skewed at all?
The question was about the inclination of the orbit of Ceres with respect to the Earth-Sun plane. The main asteroid belt, the asteroids have a range of inclinations. So Ceres is not unusual in that regard. They do vary, and they've been scattered. Their inclinations are a result of collisions and scattering during the formation process. So it's not that unusual. But most of the main belt is within maybe plus or minus 10 degrees, although there's some with a 40-degree inclination. So, gentleman down here with a question.
Maybe a little early in your time of the mission, but have you learned things that would suggest you might do things differently the next time you do something like this?
The question is, have I learned? Are there things I wished we had done that we haven't done in terms of having instrumentation on board? I rephrased your question. Is that adequate? So absolutely. We wished we had a magnetometer on board, especially at Vesta, to see if it has a magnetic field, because that would confirm our interior modeling that suggests that the core is iron rich. We would look for a magnetic field associated with it. I wish we had I wish I could detect diffuse material that would come off the limb, diffuse gaseous material, because we wanted to see if Ceres is outgassing, is giving off water, because there's water in the interior. If it comes up to the surface and sublimates, it would be nice to see it. I'd like to see if those bright spots are like a geyser on Ceres, but our instrumentation doesn't have the right optics to detect that. So those are the main things. And of course, I'd want to land and have a laboratory like the Mars Sample Laboratory on Ceres. Thanks for asking. Yes, ma'am.
Are there any theories about where the water in the center or under the crust comes from, or how it is created?
The question was, are there theories about where the water beneath the crust comes from and how it was created? So we generally wave our hands about this. But when material is the nebular, the solar nebula, 4.5 billion years ago, was rotating gas and dust, and things were colliding and they started sticking together, and then you get something nucleated, and then they collide and stick more, and they grow and they grow and grow. And then And so this is a material of gas and dust, and the water was there with other gases. And then if it gets big enough, then you're also collecting radioactive material. All rocky material contains some radioactive elements. And so that radioactive material heats up, and you get something big enough, and then you heat it and it melts, and then the heavy stuff sinks to the center, and the light stuff floats to the top. So it's that sort of hand-wavy process of planet formation that we think results in what we see today. So
we've probably time for like one more.
One more question?
Just since there isn't a fuel station out there to refuel with, how do you extend the mission? Do you just slow down?
Oh, okay. Since there's no fuel station to refuel, how do we extend the mission? So our extended mission will go until we run out of fuel. So we've planned to use some fuel in the low altitude orbit, and the engineers did such a good job that I think we're going to have leftover fuel. But we're not going to leave Vesta. We're not going to leave Ceres. We'll do something else in Ceres orbit, and we have to, for planetary protection, because there is water, because Ceres is a watery body, we do have to park the spacecraft in a safe orbit that will be stable for hundreds of years so that we don't contaminate the surface of Ceres.
Doctor, the weight of Dawn, the orbital weight of Dawn.
Of the spacecraft, what's the weight of the spacecraft?
Yes, Doctor.
Hundreds of kilograms? I'm not really sure. I'd have to look that up. So I'm sorry I don't have that answer.
It's listed on a fact sheet on NASA.
Yeah, if you can find the fact sheet, we'll list it. But I know the 100 kilograms of fuel, and that's going away. So the mass is continually decreasing as we use up the fuel.
Won't eventually a crash, though, when you say hundreds of years, I mean, does that solve that problem?
Kilometers. No, it's going to be in a stable orbit.
It's just
Put it in a stable orbit. Yes. One last question.
Okay, yeah, we'll do one more. And
How long does it take you to sending a signal and get it back?
Oh, how long does it take to send the signal and get it back? Oh, I didn't do that calculation either. Those guys at Goldstone take care of that for me. I'd say 20, I think it's about 20 minutes. But you know what? We better calculate that because we're 3 times the distance. And this is how I did it, but please check me. The Earth is 7 minutes from the sun, light travel time. And then Ceres is about 3 times that distance from the sun. So the spacecraft's at 3 AU, so I said 7 times 3, about 20 minutes. But I'd really appreciate it if someone checks my arithmetic.
Thank you,
Okay.
everyone, for coming in.
Thank you.
This has been a presentation of the Library of Congress. Visit us at loc.gov.